An overcurrent relay is said to overreach when it operates at a current higher than its setting, equal to its setting, lower than its setting, 2/3 of its setting. So when is the relay supposed to operate? The relay is supposed to operate when the current exceeds the setting. Operates when current exceeds a set value, preset value. Okay. Now when do we call as overreach? So when the relay, it is operating when it is not expected to operate, that is overreach. Okay. So that means if the current is lower than setting, even when in that case the relay is operating, then we call it as overreach. So it is option C. 3 sections of a feeder are provided with circuit breakers CB1, 2, 3, 4, 5 and 6. For a fault F as indicated in figure, you have given options. Okay, and this is the given figure. Now we will see how to approach this problem. So here the source is not given, only some part of the feeder is given. Okay, now the fault is occurring in one of the feeder. Okay, so what would we want here? This feeder should be completely isolated. That means CB5, circuit breaker 5 and circuit breaker 6, they both should be tripped off, and that too immediately after the fault occurs. Okay, and what about the other circuit breakers? The other circuit breakers, they can stay intact, right? So now we will go through the options. First option is circuit breaker 5 must be set to trip after circuit breaker 1 trips. This is absolutely wrong, because circuit breaker 1 should not trip, only circuit breaker 5 should trip. Okay, then circuit breaker 5 must be set to trip after CB3 and CB4 trips. This is also wrong for the same reason. And CB5 must be set to trip after CB2 trips. This is also wrong. CB5 must be set to trip before CB1, 2, 3 and 4 trips. So this is what we discussed, right? So this is the right answer. It is option D. Consider the protection system shown below. All circuit breakers are identical. A single line to ground fault with zero fault impedance occurs at the midpoint of the line at point F. This is point F. But circuit breaker 4 fails to operate, stuck breaker. If the relays are coordinated correctly, a valid sequence of circuit breaker operations is. So you have various operations here and you have the diagram as well. So we will see how to do this problem. Now when the fault is occurring in this transmission line, what is the ideal thing? The circuit breakers that are delivering to this line, they should be broken off, right? They should be tripped. So these circuit breakers are 4, 6, 5 and 7. Now what is happening? The circuit breaker 4 is stuck. Okay, now what is the correct sequence of operation? Now the first one is, anyways it is there, 5, 6 and 7, they should be tripped off immediately. Okay, now if 4 is failing to operate, then what is the next possible thing? Here the power can come from here, as well as it can come from here as well. So 3, 1, 2, all of them they should operate. Okay, but first 5, 6 and 7 will operate, and because 4 has failed to operate, after a while, after a certain delay, 1, 2 and 3 are going to operate. So what is the correct option here? This is option C. A 3-phase transformer rated for 33 kV, 11 kV is connected in delta star as shown in figure. The current transformer's CTs on low and high voltage sides has a ratio of 500/5. Find the currents I1 and I2 if the fault current is 300 amperes as shown in figure. Here you can see the diagram. The primary side, the transformer is delta configuration, and the secondary side it is star connected. Okay. Now what is the information first we will write, right? So what we have, the transformer ratings we have 33/11 kV. That is the line rating. So on the line, if 33 kV voltage is on the primary side, then you're getting 11 kV on the secondary side. And also the CT ratio is given. That means if this is the primary, this is line current IA, it is going to be primary, let us say. If it is 500 amperes, then 5 amperes will flow in the CT. Okay. Now the fault current, this is the fault, right? Fault current is given as 300 amperes. Now what we have to find? We have to find I1 and I2. So first if you write down the ratios, right, 33 kilovolt by 11 kilovolt, this is the transformer ratio, and the CT ratio is 500 by 5. Now you can see that if the fault current, it is flowing like this, what will be the current in the other two phases? This is going to be 0. Now if 300 amperes is flowing through here, then what will be the current in this? This we will get from the turns ratio. So whenever you have a 3-phase transformer, be careful whenever you are applying the turns ratio. Okay. Here the line voltage on the primary side, this is equal to, this we will take as VL1, line voltage on the primary side. This is equal to the phase voltage on the primary side, and this is equal to 33 kilovolt, let us say. And what about the secondary side? The secondary side VL2 is given, but this is equal to root 3 times the phase voltage on secondary side, and this is equal to 11 kilovolt. Okay. Now how will you find out the turns ratio? N1 by N2. This will depend on the phase values, right? So N1 by N2 is V phase 1 by V phase 2. This is going to be equal to VL1 by VL2 by root 3. Okay. And this is what? 33 root 3 divided by 11. This is the turns ratio. That is what you have to apply when you are finding the current. So if 300 amperes is flowing through this, then the current through this, if you take as ICA, then what will be ICA? ICA by 300, this is going to be N2 by N1, which is what? 11 by 33 into root 3. So ICA you are going to get as 100 by root 3 amperes. Now no currents are flowing in the other two phases, right? So here also there will be no current flowing, right? Transformer, if secondary current is not flowing, primary current will not flow. Okay. So what will be the current flowing in this line? The line current is not going to be 0, it is going to be equal to ICA, because here if you apply KCL, ICA is flowing like this, no current is here, so it will, all of the ICA will flow through this. Now if ICA is flowing like this, then what will be the current? I1. This you can find from the CT ratio. ICA divided by I1 is equal to 500 by 5. So you will get I1 is equal to 1 by root 3 amperes. And what about I2? I2 you can see this is the CT of this phase. And what is the current through this? This is simply 0. So I2 is going to be 0. Okay. And I2 is equal to 0. So these are the final values.